Okay, so we're going to continue with our lecture. Hopefully, our guest is recorded because I cannot guarantee sometimes the system, for whatever reason, it doesn't record. So um, it is actually better for you guys to be here to learn. But if you um, want to leave, feel free because the lecture is supposed to be recorded, but I cannot guarantee. So if it's not recorded, then you would miss the actual lecture. But again, I'll try my best to record it. The reason that I said I want to record this because a lot of students, so a few students told me that you guys get tired in the next like half of the class. So I thought this will give you a chance to be relaxed during the class, that you can you can review the lectures afterwards. I saw my son was double playing the speed at double. I'm playing the video at double speed just to get the thing that he wanted. Anyway, so I think today's lecture is probably one of the most difficult one. And then later on, of course, we still have a lot of equations, but a lot of them are going to be much more straightforward. But today's one, because we have to manipulate between like different terminals and then different directions of currents and things like that. So it really becomes quite difficult to understand. But I think if you get to understand what we have today, you're probably going to be going through the class okay. And I want to emphasize again, to study this class, the goal is really for you to memorize all the equations because there's so many. There's no way I can memorize, so I wouldn't expect you to memorize. So the most important aspect is to understand the concepts and the procedures to derive those equations. So, and then once you understand the procedures, how to do it, and it's naturally like getting to solve problems very easier. And then another aspect that if you write an equation on a piece of paper, it not only enhances your memory, but also it pushes you to think, okay, how do I get this equation? How do I use it? If you simply go to the book and copy equation, it has no value because you don't know where to use it, how to use it, and how to get it. Right? So the process of writing this down is to help you to really to enhance your learning. So that's why it's important. Now, I did have a few students ask me today during office hours saying, okay, how do I study to prepare for the quiz? So I think the most important thing is that because we have a textbook, so it's good that you read the textbook. We don't cover everything from the textbook, but pretty much, we cover most of it. So it's good to read textbook and review the lecture, and especially since the last lecture, I started to record it. If you have trouble to understand some parts of the book, go back to lecture, see how it was solved, and then do the homework. See, the reason I give you the homework is the in-text exercises. It has advantage because it usually follows right after concept is given or example is given. So you read the section, you do the exercises, and again enhance your learning. So instead of finishing the whole chapter reading and then go back to the homework, my way would be just read the section and do it, and to see how much you understand it. And then once you got the chapter finished, you did all the homework, and then you will go back. Okay, now I know what's going on with the whole thing. Now I go back to see whether I really understand what I did in the past couple of chapters. Couple of sections of the problems. So if you read the book, review the slides, do the homework, I'm pretty sure you can get 80, 90, 100% on all the quizzes. So that's the way that I wanted everybody to do. But of course, I do see a few people get like 2 points, and even one person got a 0. That's probably never studied or never understand it and never understood the content, even if you studied. So that's probably what I can guess. And then ideally, all students need to spend 9 hours outside the classroom for each class like this, for an average student. I mean, right? So if you take a whole semester, 4 classes considered as a full-time student. That's 12 hours of lecture times 4, that's 48, right? So that's reasonable. Average student would do. But if you do really well, then you might not have to spend that many hours. But if you do a little bit behind, or your prerequisite wasn't done very well, you might have to spend more time than that. So that's how it works. Going to school is like that. You cannot complain 40-hour week, and students work 60 hours a week on class. I mean, if you have families, you have kids, or you have another job, that might make your learning even a little bit more difficult, right? So it's all, everything is together. But another thing, of course, let's say halfway through the semester, you feel that you're really behind, you cannot catch up. I think you still have a chance to withdraw the class, but prepare for next one. So the thing that I really don't like is that if a student like get, say, 20-30% in the whole series and still stay in the class until saying, take a chance, say, oh, I'm going to do well in the final, I'm going to pass the class anyway, that's not going to happen. It never happens, okay? Never happens. It might happen 1 in a million. So if you really do really poor and you cannot catch up, you don't have the time to invest to the class, the best way is probably to withdraw at some point. I'm not saying that you need to withdraw, it's your choice. Because I mean, if you get an F in the class, you really waste your time, your money, or the tuition and everything that you invested. It's really bad, right? So again, just plan yourself. My goal is not to fail any student, but if you do fail the class, it's probably something, let's talk about it. Don't be afraid to see me. We can discuss your options. We can discuss how you can catch up moving forward in the class so that we don't, So, okay, so today we're going to continue with the current murals. I might not be able to finish all the stuff today for chapter 8 because there's a few different, very difficult derivations. I really want to get that out to you. So I might run slow at some points just to make sure that you understand the process. But once we got that point, then it will be easier moving on in the future. So if I cannot finish it, then we'll spend a little bit more time next week to finish up chapter 8 before we're moving on to chapter 9. So last week we talked a little bit about the small signal equivalent circuit of current mirror. You already understand, we built a current mirror to replace resistors. So it provides a better biasing circuit, smaller footprint for us to design our IC. But even though the circuit is supposed to provide a DC current, biasing current, reference current, however, you imagine that eventually we're going to use the circuit for small signal amplification. So when we use the circuit for small signal, a small signal is going to be added on top of the DC biasing. So that's why here you see IDY is a reference current. We add another I, a small lowercase I, to show that at some point you're going to see a small signal added to the reference current. And once that added, this whole circuit, we want to understand how does it perform in terms of this small signal, right? So to understand small signal, we need to draw the small signal equivalent circuit to understand it. So in this case, we're going to have to draw the small signal. But when we draw the small signal, look at it here. So there are two currents added together. So what like to do is superposition. So we just neglect the DC current because it's like an open circuit, but this AC current in parallel. So it's like two current in parallel, right? One is DC and the other one is small signal. So we're going to just leave the small signal there, and we're gonna do just a small signal, and then we're gonna ground it, because you see this one eventually is gonna go to VDD. So for a small signal, it's gonna be ground. And moving down, we have Q1. Now Q1 has this gate and this source, right? So then we have this current, and then there's going to be its own internal resistance R01. So this is a small signal for this guy. But then we have gate and the drain. So what we want you to do is, before we move on to second one, we want to see how the connections are done. So by looking at this circuit over here, can you guys tell me, like, if I circle this as a stuff MOSFET, can you tell me which ones connect to which? When you look at here, that's the source, and source is connected to ground, right? So we can connect to the ground. How about the gate and drain? You see, gate and drain are connected, right? Right. So then source is grounded. So that's, we got this Q1 plotted. And now we're going to plot Q2. So Q2, we're going to plot the gate, and then also the resistance. And here is our output is like, now output is like over here. See, the output is right here, and the output is here. So for Q2, and we look at it, what is connected to the source with also ground, so we can ground that. How about gate? Where is the gate connected? So we can connect this to ground, which means this is going to be like this, connected, right? So what is connect to the gate? The gate is connected to the gate of Q1, and the gate Q1 is connected to drain of Q1. So therefore, we would simply connect these 2 points. So this is like a process, right? So we connect it. So this is G2, D1, and D2. So now we have this whole circuit plotted. What our next step will do is, you look at this current. So the current over here is flowing from ground to the drain, right? So the ground is on top of there and coming up. So we can simply move it so that it look better. So our eyes will be more pleased if we move that current to like this. So it's going to be up. So this ID, and it's ground, and it's going to the so this is ID, and this is going to be our GM times VGS1, and then this is going to be GM times VGS2, and this is our G, and this is our S. Okay, so you see, we did nothing here except that we moved the ID instead of hovering on top. We simply move, because that ground and this ground can be connected, right? So we'll simply move here. So we got ID, we got this one, we got this one, and from here to here is our VGS. So if from here to here is VGS, and this is GM times VGS, remember what we can do? We can convert this one into a resistance, right? Because voltage divided by current give you a resistance. So this really, even though it looks like a control source, but eventually it becomes a resistance. And then this one too, it becomes a resistance. No, not this one, but this one becomes a resistance. Huh? This one? This one? In the middle? Yeah, it goes to ground, yeah. And this one goes to ground, and but this one goes up. So. Yeah. So this is the circuit that we just draw, and we would simply have this. Okay, see, we have RO1, right? Then we have GM here, but again, as I said, this GM can become 1 over GM becomes a resistance, and this GM2 times VGS is R2. So this is a very simple circuit. If you look at the circuit, the most important thing we want to find out is what is the, we don't, like at this point, we're not very much interested in the gain per se, but we're most interested in looking at the output resistance. So we're going to look at output resistance. You know, if we want to, let me see how many slides that I can use so that yeah. All right. So I can move down to, so look at here. When we look at output resistance, what we need to do is simply just open the current source to see what we have. When we open the current source, basically here, there's no current in this whole branch. And then this whole branch becomes nothing. And therefore, no current here, VGS 0, and this is 0, and this becomes open. So therefore, your output resistance is simply like, yeah. So your RO is simply RO2. That's your output resistance. We can get right away, because when we open this one, this side becomes no current at all. And this becomes open circuit, the output resistance is there. Now, if we want to look for, so I already did that. So we basically open this one, and this becomes open, this becomes open. So that's why we got RO equal to RO2. So I'm gonna just skip this one. Yeah, open the, well, you don't open all the controlled current source. We open it because the current is 0, because VGS 0, and then it becomes 0. But in some other cases, you cannot open it because if it's not 0.
Oh, in that case, yeah.
Yeah.
So they all become 0 because when you open the first one.
When you open the first one, all the, yes, right, all right, yeah. So now, if you want to look at the input resistance, we would simply like open the, we can open the output and simply looking at from here, looking in. Now, because from here looking in, you can see that this part of the circuit has no impact on the primary circuit. So you take the voltage divided by the current, you get the input resistance. So it's easy to get input resistance becomes, so R in becomes RO1 in parallel with 1 over GM. Okay. So this, okay, so at this point, I probably want to do one thing. How many of you actually know the expression of this parallel resistance? How do you write it? I was a little surprised the other day that I had a couple of students coming to me, and none of them could write the result of this. Right, so it's basically, it's basically the product of the two resistance over the sum of, of course, you can manipulate the different form, but that's the basic idea. You have two resistors in parallel. That's how it works. Okay. And then one of the things that a lot of times we do is to look at a short circuit gain. Now, in the future, you might hear two things. One is what we use most in this class is voltage gain. So when you look at voltage gain, the ratio is like, it's called AV is VO over V in. And this is called voltage gain. And voltage gain is in the value of volt per volt. So you have input is volts, output is volt, voltage gain. Now, current gain refers to a short circuit current. See, when you have open circuit, you can have voltage. But when you have a short circuit output, what do you have? You don't have voltage, but there could be a current. So what we're looking at is a short circuit gain is, we call it IS. instead of AV. So it's going to be IO or I in. And this is in the unit of ampere or milliampere. So this is the unit of short circuit gain. So you might ask, why would you want a short circuit gain, or why would you want when do you want voltage gain, when do you want current gain? It depends on the input. So if your input is current, most of the time we want to understand the output, like current gain. If the input is voltage, we want the output to be a voltage gain. So this is in general. However, in the future, I think it was chapter 11 or 12, when we look at feedback, all of a sudden we say, oh no, actually there's only two popular ones, but we could have transconductance, which means if you have input is current, but output is voltage, what happens? Your gain is voltage over current. So that has a unit of volt per ampere or ohm. But we don't use ohm because it's a gain, right? So, but if we have input is voltage, output is current, so current over voltage, you get transconductance. The output is ampere per volt. So it's like a Siemens, right? But we use ampere. So but in this case, the reason we want short circuit gain because the input is a current. Okay. Now I can go back in here. It's easy to look at it. Why do we look at the current gain? Because in this case, our input is a disturbance at the reference current. So the small signal is a current. So therefore, we are more interested in the current gain. Okay. So now we go to look at the current gain. Let me see. We can start to. So as I said, when we look at current gain, we short the output, and then we supply a current at the input. So we supply input at II, we short the output, and then we look at the ratio between output and input. Now, since we have II, these two resistors are in parallel, give you the input resistance, right? So we can get VGS. So the process is that we get VGS at the first step. VGS is going to be II times that input resistance, which we already showed in the previous slide, which also show here is RO1 in parallel with GM1, 1 over GM1. So it's VGS. So now we know that, so from VGS, we can get the current over here. And since we short the output, do we have current in RO2? Why not? Because it's shorted, right? So both ends are ground, so there's no current. So therefore, what is your output then? Current? It's GM times VGS. So in this case, it's GM times II times I in. So our current gain will be IO over I1 equal to II equal to GM times I in. So we got the gain with the current gain. Okay, so we don't actually use this very much moving on. However, I really wanted to understand the process, how to get this gain. So for any circuit, you can get the gain. The only reason we get this gain is in the future, when we study small signal like a disturbance, when we want to understand if we have an input disturbance coming in, how much disturbance we get output, right? So this will tell you that if your input has a disturbance, like 1 milliamp, for example, and 1 milliamp may be too big. Let's say 10 microamps, and if your output is going to be say 100 microamps 10 times, you have trouble because you amplify too much, right? So that's why we need to look at here to make sure that this number is small. Now, usually this GM is in single digits to like tens. Most of the time it's like 1, 2, maybe even less than 1 or maybe 10 So depending on the circuit. And then this R in, as previous slide, we know that R in is 1 over GM in parallel with RO1. Now, RO1 is in kilo ohms, even tens of kilo ohms. But GM is a small number. It's like 1 milliamp, for example, milliamp per watt, and then the reverse will be like maybe a few hundred ohms. So a few hundred ohms in parallel with a few kilo ohms, a few 10 kilo ohms, basically you can ignore this one. So most of the time, this R in is approximately 1 over GM. So now you say, okay, so IS is GM times 1 over GM equal to 1. That's a beautiful number. So we went through a whole process, we found, oh, the gain is only 1, approximately 1. It's not exactly 1, but approximately it's slightly less than 1. So which is good. Yeah, they could be different.
They are the same.
Yeah, they're the same, yeah. But usually when we have matched resistance, especially in current mirrors, they're matched, always matched, right? So they all have the same GM. So this is how we get the short circuit gain. So again, here we can, so the beautiful step, we're going to use it right next, is that once you have that kind of circuit, we can basically say, well, this whole thing is like after all the analysis, we can represent that circuit with a simple circuit, looking at input resistance, gain, and output resistance. If we can pretty much derive an equivalent circuit of any device or any amplifier. So this will be, so this, remember this circuit on the right hand is very useful for our small signal analysis. Now, you might say, oh, this is very similar to the pi model. Well, yes, it is, but this is not the pi model, okay? Remember, this is not actually the pi model. This is actually an equivalent circuit of a more like a complex circuit. In fact, at this time, this is more like the current mirror. So we can, I can probably write down this one for you, but we probably don't have to. So this is eventually is 1 over GM. So RO is equal to RO, and A1 is equal to 1. So this is a approximate value of this one. You can go back to find the exact expression for this. Right. So what we did is from here, we come to here. Now this one is sometimes confusing, especially for beginners. Is how can you convert a current source into a resistance? In fact, you cannot. Most of the time, you cannot. The only way you can do it because we know the voltage and we know the current. With the voltage divided current, we get resistance. In this case, we know the resistance. I mean, the control source is the same using the actual input voltage. So that's why we can get it that going. So so in the future, when you see GM times VGS, if you automatically convert it into 1 over GM, I would say 50% of the time you will be wrong. You cannot do that for every circuit. You can only do it for if the VGS is the terminal voltage. Okay. All right. So now once we have this current mirrors, we can go back to analyze our basic gain cell. Let me redraw what we had in the past. I want you to compare. Okay, so I don't overlap. I can draw it here. We had the basic common source amplifier was like this. Right. So that's our common source amplifier. So we ground the source, we supply VDD, we use resistance to bias the MOSFET, and then we input at the gate. resistance that we set is not good for biasing. So now we replace that with the current source. So this circuit becomes this circuit. Then we can find VO at this point. So before we do that, so let me show the recurrent circuit over here so that we get a better understanding. So what's this circuit? We have so now we know that VO is going to be minus GM. It really bothers me. Yeah. Okay. So VO is equal to minus GM times VGS, which is V in, and then times RO in parallel with RD. So A, V is equal to VO over V1 or V in gives you minus GM times RO in parallel with RD. So this is what we have for the regular regular gain circuit. Now for this one, we don't have that resistance. So in theory, if you draw the equivalent circuit, it will become something like this. So this is what we have. So if that current source is ideal, what is your output now? If your current source is ideal, so your output will be VO will be just GM times VGS times RO minus, right? So this, yes. So your gain is AV is equal to minus GM times RO. But if this current source is not ideal, like it was previously derived, this thing has output resistance. Remember the current source for this one from the previous slide? It has its own output resistance. So basically, we can replace that here, saying that yeah, this got its output resistance, and then go to ground. So if that goes to ground, so you see what happens is that you have one resistance to go here and another one to ground. We basically can move that one to here. So because it goes to ground, right? So that resistance, this one, becomes parallel. So and then eventually, if it's an ideal case, you still have this RO, let's call it R2. So your gain will be minus GM times RO1 in parallel with RO2. So this is almost exactly the same as this one, except that RD is replaced by RO2. But that RO2 is the internal resistance of the MOSFET, which is part of the silicon. Therefore, it's not like a man-made resistance. Therefore, it's easier. So this two has identical expression. Yes. What is that? Cost? What is constant value? I thought you heard cost. It's a significant reduction in cost in terms of IC design. No, the constant value RO2 is what we derived. Is a resistance, early resistance of that idea, that current source. If I go back to show you what we had here. See here, we had RO, which is RO2, which is exactly this one here. Yeah, that's the current source we got. Okay, so now if we got a BJT, the only difference is you have R pi. Well, because current goes down. So if current goes down, your voltage here is negative. So current goes up here.
Oh, okay.
This is ground. This is ground. So current goes because this goes down, this current goes up. Yeah, so it's a negative voltage. Yeah. Okay, so if we have a BJT, the process is very similar. Okay. So the BJT, the only difference now, I'm not going to redraw the traditional with the resistance. It's going to be the same thing. But over here, you want to draw the equivalent circuit with R pi. And also here, you want to draw the RO2. And then there you have GM times V pi, and this is R pi. And this is your wheel. So you can see here, even though you have R pi, but the gain is basically the same as the previous one, because this is like a common base, common emitter. The only difference is if you look at the input resistance here, and can you guys just look at it, say, what is the input resistance? R pi. And so your gain is going to be minus GM times RO1 in parallel with RO2. And your output resistance, basically, it's going to be RO1 in parallel with RO2. Because when you have an output resistance, you would short the input voltage, short the voltage, right? So this whole circuit is gone, and this is no current here, right? V pi 0. So this two in parallel is your output resistance. Now I forgot to do the other one. So this one, same thing. So you can look at R. In this case, what is your input resistance? Infinity, right? And what is your output resistance? It's going to be RO1 in parallel with R2. Now in this case, the actual circuit didn't have RO2, but we can always add it. Yeah. No. Okay. So I want to make sure we go smoothly. So now this is MOSFET common source amplifier with ideal current source. And in the book, it did not include this RO2 because it saw the idea. Now I started to talk about idea, then we said the non-idea, then we had this RO2. So that's how we got this expressions here. Now, how would you see that is actually through this example. You see, in this example, the bottom one, we have input, and then the Q1 apparently is your amplifier. But what is the Q2 here? So basically Q2 is a representation of your current source. So later on we have some circuit. So basically, if you want to add this more like to here, and then you like this, right? So this becomes a current source. So basically we neglected that part and simply leave Q2 here as a current source so that we can analyze the circuit. Then we can still do the so now basically we can do the equivalent circuit. So we can do the equivalent circuit like this. So the bottom one has the input, Vi, and that's your terminal G. And this is ground. And here we have RO1. This VO at the middle. So that's the bottom one. And then now we go to the top one. The top one is the PMOS. So it has its drain also connected to this drain, which means we can go up like this. And then this one has this the only problem is Oh, let me write down. So this is S1, G1, and D1, and this is D2, S2, and G2. So the only problem you look at it is where is G2 connected? So in the example here, the G is a capital VG, which means the DC supply voltage equivalent. So basically we ground VG. Right? So this is very important, is we ground VG. So we ground VG. Now we have this two. It's more like, so if you look at the voltage over here, this is GM1 times VI. And then this is your GM2 times VGS2. So the only thing is now we need to figure out what VGS2 is. And VGS2 on the original circuit is VGS2 GM. And because VG is grounded and the source is also grounded, VDD and VG. So yeah, so VG2 basically grounded and source is grounded. So VGS2 is 0. Okay, so that's why. So VGS2 is 0, which means this is open circuit. So now if that is open circuit, we can further redraw the circuit to look at something look like this. Huh? They are both DC voltage, so they're ground. We're both grounded for AC. Yeah, yeah. So now you can see that RO2 is also connected to VD1 to ground. So RO2 from here to ground and this to ground. So we can move that one up to here. So we have RO1, RO2. So if you look at this one, you might already surprise that, well, this is the same as we derived from the previous slide. Yeah. So this is the ideal case where you have this. So I do have this equivalent circuit that I redraw here. So there. So this is how they redraw the circuit. So now based on this one, we can easily derive again our gain and input resistance is infinity, and output resistance is RO1 in parallel with RO2, and our gain A V is equal to minus GM times RO1 in parallel with RO2. Okay, so if we use all matched transistors, you would say, okay, if we use matched transistors, if matched, and then RO1 and RO2 are going to be the same. The RO1 equal to RO2. So in this case, how much is RO1 in parallel with RO2? What do you think? If the two resistors are the same, they're in parallel. Huh? Half, yeah, right. So it's going to be half RO. So therefore, your gain AV is 1/2. So basically, if this transistors are matched, you would have the gain reduced by half from non-ideal, from ideal to non-ideal. So if your ideal, you have a gain at 100. Now, once it's non-ideal current source, the gain is reduced by half, only say 50. So this is our current source amplifier. I think so far really everything should be looked okay because it's really straightforward. So I'm going to do example, and using this example, and we're going to look at different aspects of this derivation. And then after example, because we went down, that's the most difficult part I refer to is after this example. In this example, actually, is pretty easy. So in this case, what we want to do is to compare these two circuits and look at why we wanted to replace this resistance with the current source. Now, if you look at the current source here, is these two transistor amplifiers are the same, but the top one has a current source, but the bottom one has a resistance. I'm going to look at what is going to make a huge difference. So before we get into that point, we're given VDD 1.8, VTN, VTP 0.5, K is so K A is 400, but KP is 100. So in some of our examples in the book or in the homework, you'll find that a KP sometimes is given on purpose, not the same as KN. So you have to be careful over there. And VA is 5, which is early resistance to find early resistance. And I reference is 100 microamps, which is this case 100 microamps, which means 100 microamps over here. We are going to have VOV at 0.2 for all transistors. So now we want to find the W over L ratio of this example in the book. So if you, so what I'm going to do is I'm going to have to move on because this is what I don't like, these digital screens, because they're too small. I like the long blackboard so I can have one figure and then I can continue to write. So I have to skip this one so you guys can, so now, so over here, we're going to solve for the W over L. To solve for W over L, we know that this VOV is given 0.2 volt, of course. And then we know that this VGS, or in the other case, how do we calculate VOV? For MOS, it's VGS minus VTN. So VGS equal to VOV minus plus. So VOV plus VTN. So in this case, VGS is VOV is 0.2 and VTN is 0.5. So this gives you 0.7 volt. So we got this first step. Now, in order to calculate the ratios of W over L, we need to get to this equation. Okay. So over here, you see K is given, VOV is given, and ID1 is given. You plug in all numbers, you will get your W over L. The only thing that you have to be careful is units, because sometimes it's milliamps, sometimes in microamps. If you want to use milliamps, use everything milliamps. Or if you use microamps, everything microamps, and you will be good. So in this case, you have ID1 is 100, right? So 100. So we can use 100 micro. So if you're not sure, you can leave the unit there. On 1/2, K is 400 micro as well, W over L. And then VOV is VGS, VOV is 0.2 squared. Yeah, so we didn't actually use VGS, we simply use VOV. So this will give you W over L of 1 equal to 2.5. Now, there are two ways to get W over L of 2 and 3. They are both PMOS, they're both the same. One way is to look at the K ratio. The K ratio is 4 to 1. So therefore, this one has to be 4 times larger than the other one. And then the other way to do it is, do the hard way is to look at the, so this is going to be KP instead of KN. and W over L, this 2, and times V over V squared. And then now you plug in the numbers because Kp is 4 times smaller, so W over L is going to be 4 times bigger. I believe it's 50. Yeah, it's 50. Why is this 4 times? Because Ka is 400 and Kp, 4 times Kp is 400, right? So Kp is 400. So we got number 1 resolved. Now we need to go to number 2. Number 2 asks you to find the small signal voltage gain. So the small signal voltage gain, remember, if we go back to the circuit over here, we need to find GM, and we need to find RO1 and RO2 so that we can plug in to this equation to get it. So we know that GM is equal to, and now this is something we have to go back to like chapter 5. So GM is equal to 2 times ID divided by VOV, and 2 times ID is 2 times 0.1 divided by, that's 100 micro is that, so we had 1 milliamp per volt. Now, if you use like 1000 microamp per volt, it's also okay, but apparently milliamp is kind of the conventional unit in microelectronics. Like in circuits, you always use ampere and volt, but in microelectronics, we always use milliamp and volts. So this we got GM, and then we have to calculate RO1 and RO2. So RO1 equal to is VA over ID. So VA is 5 over 0.1 milliamp. So you get 50 kilo ohms. And that is also the same as RO2 because they have the same biasing current. So now you can look at AV is going to be minus GM times RO1 in parallel with RO2. Now GM is 1, RO2 and R both 50 in parallel to become 25. So you get 25. Don't forget the minus sign, 25 volt per volt. So that's your small signal voltage gain. So the next thing was looking at how to find the, let me see, the number 3 is to determine the allowable range of signal swing. Now let me explain to you what voltage swing means. Let's say you have an AC on top of a DC signal. So if we have like this, a purely AC, you can do this. Now if you have add this AC on top of a DC, it becomes something like this. So between the maximum and minimum, this is called a swing. For the second case, you know because our AC is on top of this DC. So if your DC volume, let's say it's too small, you remember what we already explained. What happens to the AC signal? The bottom part gets cut off. So you don't get a purely a waveform. So we need to find what is the minimum and what's the maximum. So in this example, if we look at VO, what would be the minimum of VO? Can VO reach 0? Let's say if VO reach 0, what happens? So your VDS, you're going to be smaller than VGS. So therefore, you cannot really get to 0. Now, what is the minimum though? The minimum is this VDS1 minus VDS1 has to be larger than VGS1. GS minus VTN, which is VDS has to be larger than VOV. Well, in this case, you already know VOV is 0.2. So therefore, our lower range is 0.2 volts. Okay. Now, okay, now for the upper range. Our upper range apparently is limited by VDD, right? Can all VO reach VDD? Can we all reach VDD? Similar. You cannot, because if VO is VDD, what happens? So your VDS on the top one is 0, which is less than that VTN or VTP. So therefore, you run out of saturation, right? So therefore, in order to keep the top one also in saturation, we need to make sure that VDD, so that's lower, and then top. Top is Q2 needs to stay in saturation region. So it's mixed. So therefore, we have VDD here. So VDD minus VO has to be larger than has to be larger than 0.2. So VO has to be less than VDD minus 0.2, which is equal to 1.6 volt. So our swing is going to be from 0.2 to 1.6 volt. And the middle, this is what we're going to use the next slide. The middle is going to be 0.2 plus 1.6 divided by 2 equal to 0.7 volts. So what it really is saying here is that if we come to this figure, what we are saying is we between 0.2 and 1.6, and the middle is actually 0.9. The middle is 0.9 volts. So that is kind of our amplifier in the future. What can do maximum for you? So if your input is say certain millivolts, after amplification, you get up to between 0.2 and 1.6. So if your voltage is more than that, and your top is going to get cut off, and your bottom is going to get cut off. So your output is not going to be a sinusoidal waveform. So we got that. Let me see. Now we go to the next step is looking for. Oh yeah. So if the current source is which basically look at this other circuit over here, is if this thing is going to be replaced by RD, and what happens? So it's basically the same thing. Instead of using the current source, we're not going to replace this RD with the current source with RD. By doing that, we know that the gain of this circuit is going to be VO over Vin. Okay, so AV is going to be minus GM times RO1 in parallel with RD. We're not going to go back to derive everything, but we know that this is. But if you have a doubt, you can always draw the small signal equivalent circuit. Now you right away you will get this solution. Now in order to give this to 25 volt per volt, we know RO1 is 50 and GM equal to 1. So therefore, how much RD do we need? I mean, not 25. We need the total to be 25. So we basically will need the RD going to be 50 kilo. So basically, what we're saying, the first thing is that instead of the current source, if we replace it with resistors, we will need the resistor to be at 50 kilo. It's quite a big resistance. The second point is that we need to maintain the current. So current ID is 100 microamps. So now, in order to maintain this voltage VO, to be between 0.2 and 1.6 volt, middle with 0.7 volts. Like that's the middle we need to get. So now we need to get this VO, capital VO is going to be VDD minus ID times RD, which is going to be VDD minus ID is 0.1 milliamp times RD is 50 kilo ohm. So this VO is between 0.2 to 1.6, so, and the middle is 0.7. So therefore, we have this VDD minimum has to be VO plus ID times RD, which is 0.7 plus 0.9. Again, I made a mistake again. So 0.9. I don't know why I always get 0.7. 0.9 plus 5. It's going to be 5.9 volts to maintain the same operation. So now you see two disadvantages. One is that resistance is too big. Secondly, the voltage has to be much higher. The previous example, only 1.8 volts. But in this second example, you're going to need 5.9 volts, which is much, much higher than what you need. So this is not good for, it's not good for our like IC design, because the voltage, the smaller the voltage, the better for everything. The higher voltage, you need a more like a, it creates more problems. Okay, so yeah, so okay, actually I already did it. Now, you already find that with this top circuit here, if the current is ideal, we have the gain is going to be GM1 times R1. But if the top is not ideal, the current source is not ideal, we reduce the gain basically by half. So the question that if we increase the up part resistance, we can get the gain to be increased. So if this one, we go to this to multiply by a K, then we get this resistance to be K times R01. If K is less than 1, your gain, of course, is going to decrease a little bit. But if your K is larger than 1, your gain actually increases instead of decreasing. But of course, in real life, having K larger than 1 is very difficult. I wouldn't say impossible, it's very difficult. So in the next following on, that's what I call the most difficult part, which we're going to design a circuit to increase the thing. Basically, we get increase the K. So we're going to look at how we do that after the break. Is a common gate amplifier. Okay, so let's take a quick break. Come back at 5. Okay.
Two attempts.
Yeah.
And I got a lower one on my second attempt. And then it's graded as my lower one. Is that gonna stay like that, or is it gonna take my higher one?
I don't remember what I did in the, it's how set up. I think it takes the second one. It takes the second one. So which maybe if you did lower in the second one, it will be your second one. Yeah.
It doesn't take our highest score. Usually that's how.
Well, it depending on how I designed the problem in the beginning. I mean, I don't remember what I did. So if I did it like take the second one, it's gonna be your second one. It's not gonna take the high one. Yeah, I cannot change it.
I wouldn't have taken this. I wouldn't have taken it again.
Well, I mean,
I was just doing stuff to do stuff like.
But
just to see.
yeah,
Like, yeah. Because I got.
yeah. Yeah, I cannot change after the quiz is taken.
Well, actually, it says 8 out of 10 there.
Well, that's what I'm telling you. I do not know what I did in the quiz. I cannot change after the quiz is already taken. So if I said take the highest, it take the highest. If I said take the second one, it take the second one. But I cannot change after the quiz is already taken.
Gotcha. And
Yeah.
how are we supposed to, is there a way to check like,
Yeah, you check your grades. That's,
no, sorry, is there a way to check if it takes the lowest or the second one or?
no, you simply check your grade book. The grade book will show you what you have. Okay, you do grade book shows the second one, shows the highest one, the highest one, okay?
Even though it's late,
Yeah.
you guys are running.
Yeah.
Anyway, I think we're definitely-
No, well, I emailed 3 times the grades. Times. I emailed many times and asked, so I cannot.
Just grab- Barely.
Well, like we dropped 1 or 2 quizzes, so you get an opportunity to do better in the future. If I didn't notice you, I would, have excuse, but I announced many times. I even won this morning or yesterday.
I was saying, I
Yeah.
didn't know I was gonna be late.
Yeah.
Okay.
Yeah, yeah, try to do better next time. Okay. Oh, yeah.
Are they gonna be consistently at this time, or was it just this time?
I think we'll do it consistent at this time because we got people doing the PAC. It's very hard. We don't have people. I used to do random quizzes, but when we have people doing at the testing center, I just cannot do that. Okay, that mess up everything. Yeah, but yeah, we're gonna do it in the beginning of the class in the future. Yes,
Next week, not this week.
not this week.
Okay, so that's because you're going a little slower in
Yeah.
chapter 8. Okay, so you're just. Going, the quiz gonna be from 8.24 to the end of the chapter, or it's gonna be some chapter 9 as well?
Oh, no, chapter.
The rest of
Well,
the rest of
no, next week is what we call today, so it's gonna be part of it's gonna be chapter 8.
the last part of chapter 8 that we're doing right now.
We are doing today, yeah.
You do office hours tomorrow or not over the weekend? Do it kind of on Monday or Tuesday or something? Just Friday, right? For you?
Well, as I said, if you guys need more, just let me know, because
Well, I wanna try to start finishing the homework like on Monday or Tuesday, and so I have questions before we get here on Friday. So yeah, maybe I'd like to try to email you on maybe like Wednesday.
yeah, just email me and I'll make it happen.
So by the time we already get to Friday, I already wanna have questions answered.
Okay.
You know what I mean? Or-
I understand.
Thank you. Yeah, but it did, like, it's really, I don't want to figure out, like, I think you guys. Those are pretty good. Okay, the first one.
Okay, let's get started. And I appreciate many of you staying for the class, even though it's recorded. But my personal experience is that it's always better to be in the real world, other than the virtual world. At least if you get a question, you can ask. Hopefully, that's one of the advantages you get. So what we're going to do is we're going to look at how we can design a circuit that's going to help us to increase the resistance. So if you look at what we have here, is we have this input. In this case, it's a current source connected to the source. And there is resistance, source resistance at the source. This one is necessary because this is for biasing. Like if you don't have this one, you only have this. What happens is when you don't have a small signal, like current is an open circuit, the whole circuit doesn't work. So you cannot have an open circuit. So you have to have this resistance or something else. So this one, without AC signal, because this is current, right? When you don't have a current, it's open circuit. So we have to have something here. And then on the top, we have RL, which is load resistance. The reason we have that because we need to connect it into VDD. And of course, in the future, we can replace that with a current source as well. But for the time being, we use RL for the simplicity of analysis. And then for VG, it's not grounded per se because it's biasing. The reason we need VG, we don't ground it. Can you explain why we don't ground it? Can we ground it?
When you do small signal, the DC goes away.
Right, that's true. But can we ground the VG for DC? If we ground it will be 0. Right, if you ground VG and then for DC, if you ground it, it's going to be 0 and your source is 0, so VG is 0. VG is 0 is less than VT and it's not going to be a saturation, right? So we cannot ground it. But it's okay because for AC, it's going to be ground. So therefore, this whole thing will become a fairly simple. So what we can do is, in fact, is what the book want to tell you is that we want to represent this whole thing like this little block with equivalent circuit. Remember, we had the previous one, we derived the equivalent circuit for a common source amplifier, But now we're gonna derive a equivalent circuit for this thing. But this thing is, gate is ground for AC. Of course, the drain is also grounded, but it has resistance there. So the drain is not truly grounded, so it got a resistance at the load. Resistance, so therefore the drain is not grounded. We take output actually at the drain, so therefore it's not a common drain. So it got to be a common gate amplifier. So that's why we call it common gate amplifier. So we want to derive the common gate amplifier as a simple equivalent circuit. So a simple equivalent circuit will look like this. Like this, like for this Thevenin's analysis, you remember in the past we talk about two terminals. You can always to represent one with input resistance and output resistance. Like this 4 terminal. So here, we just want to identify where are the 4 terminals. So that input on the top is over here. So that's our input. Okay, that's a tricky part. And the output is at the D, right? Then we have ground, which is ground. Of course, the VDD is a ground in the future. So therefore, we have here, this one is really the source, the G and the D. So we have the source here, and then we have D here, then we have G grounded. The difference here is that this signaling is called IAS times IS, which in the future is input over here, is not GM times VGS. So this is something that you have to be careful. Is when we join a circuit, you say, oh, this circuit looks like a pi model. No, actually, this is not pi model, okay? This is actually an equivalent circuit of this thing here. Now, if we know the equivalent circuit of this thing here, we can now draw the whole thing starting from input. Then we have RS, ground, and then this RS connect to this yeah. Okay. So now, see, let me change a color so that we can make it better. So this is like this, and also like this. So the middle part is the MOSFET. Now, again, this is not a pi model because the pi model start with G over here, but here is not G. This is S. So this is S, and this is G, and this is D. So apparently, because that is not the pi model, so therefore, this thing here, what you're seeing here is called R in, this is called I out, and this is called AIS times I. So how do we solve? So this is the equivalent circuit that I just draw. Again, this middle part is this is the so this is the again. I just want to many times emphasize. So, but okay. So now you say, oh, this is the equivalent of that thing. And now if we know the circuit, this circuit, it would be very easy for us to find the gain, the input resistance, output resistance, everything is really simple. But how do we find the middle part? Okay, So that's the most difficult thing to do. How do you find R in and R out and AIS? So this is what we're going to do is we're going to start to draw the small signal model to figure out what this R in and R out is. So for this one, to draw the small signal model, now we need to go back to the pi model, okay? So now we're going to draw the pi model. So you're going to see the big difference. I'm going to draw them on the same graph. So to draw the pi model, before I wanted to start to draw the existing stuff. Okay, so now the important thing is to look at the pi model of this thing is that the current you can see it here is the pi model. Here's the pi model. Here is VGS, is VGS, and this is VGS. Oops. This is GM. So the thing inside the blue block is the pi model of our MOSFET, right? So our input is connected to the source and our gate is grounded. And then our output is connected to RL. Why is LL? So this RL. Okay. This looks bad. Let me erase this thing. So this is the circuit we have. So from this circuit to transfer to this circuit, we need to do a little bit of work. Is how do we find R in and R out and AIS? So for this circuit, because there's a controlled current source, and you can see now, you cannot convert this controlled current source into 1 over GM anymore because the terminal voltage is actually not VGS. And also, you need to be careful is that this RL is connected to ground, not the source, okay? So that's another thing to be careful. So, and then VGS is from here to ground. See, from there to here. But here is not ground, but the top is grounded. So we can find out that the VGS is basically over, if we find the voltage over here, if we call this like V something, I don't know what we call it, VS, yeah. So VGS is VG minus VS is going to be minus VS. That's something you can do. And we need this because VGS minus VS, because later on, we will find a VS, which is related to something like this, okay? Now, the other thing to be careful is that this IS may not be the same current in here because, see, the current going this way, and there may be a current going this way. So this current is not the same as this current or this current. So ultimately, we need to do like nodal analysis in order to get the results we wanted. So let's do good. So let's do a nodal analysis on this one in order to get the input resistance. Let me go back to the circuit over here. So for the circuit over here, in order to get the input resistance, we basically we need to open the output because this is a current input. So what we're looking for eventually we're looking at this A is the current gain. So when we look at the current gain, we basically can open the output current like the output no current, we open it, and then we apply a current over here. And to see how much we got the resistance, therefore we can get the input resistance. So this is where this circuit is coming from. So when we look at the input resistance, we didn't consider RS. So we basically took that part off. The reason we can do that is because we are, and I go back, because we are looking for the equivalent circuit of this thing. That thing, this is not part of that. So that's why we simply apply a voltage over here to find the current, and then we find the input resistance. So over here, we're going to get, we apply this voltage, and you can see that if we find the voltage Vx divided by Ix, so we apply voltage Vx, we divide by Ix, we'll get the input resistance. So we assume Vx, eventually we'll cancel that. So all you assume Ix, you get Vx either way. Now, when we assume Vx, we need just to find out what Ix is. To find Ix, we need to do a little bit of, let's say, maybe a nodal analysis on the circuit over here. So let's assume Ix is in this branch. So Ix going down, we can find the voltage over here. So that voltage over here, let's call it VO. It's going to be Ix times RL. And then we can find the current over here. Let's call it IS. So our IS is going to be Vx minus VO divided by RO. And VO now we can apply back to Vx minus Ix Rx divided by RO. Okay? You guys understand, right? So this voltage Vx minus voltage over here divided by the resistance, we got the current in this branch. So now we go back. Rx. Yeah, Ix times RL. This is RL.
Yeah, but you wrote IX.
Oh, I wrote Ix. Thank you. All right. So now we need to find the total of Ix here. See, there's a current going this way, there's current going this way, there's current going this way. So which means Ix is going to be, or if we use Ix plus Gm times VGS, it's going to be same as Is. And here we also need to find what the VGS is. Can you guys tell me what VGS is in this circuit? By observation? So VGS is the voltage from ground to here. And the voltage from here to ground is Vx. So therefore, negative Vx. Okay, so now we know that, okay, so now Is, right. So Is is given as Vx over Ro minus Ro over Ro times Ix, which we basically plug in here. Now VGS is minus Vx, so we get Ix minus Gm times Vx equal to Vx over Ro minus RL over Ro times Ix. So now you have Ix on this side, Ix on this side, Vx here. So we can use Ix 1 plus RL over Ro equal to Vx equal to Gm plus 1 over RO. We got this. So I don't have space, so let me move on to, it's going to be V in, Vx over Ix. Vx over Ix. Now we're plugging the bottom equation over here. So it's going to be 1 plus RL over RO divided by GM plus 1 over RO. Now, if we multiply RO on both sides, we get RO plus RL divided by 1 plus GM RO. I hope I got it right. Yeah. So this is our input resistance. So we got it. The thing that here is GM times RO is usually much larger than 1. So say GM is 1 and RO is 50K. So you get like 50. So 50 much larger than 1, right? So basically, if you want to do further, you can neglect that 1 to simplify it. So you neglect 1, and then you got the first term RO cancel, and the second term is that. So we got really approximately equal to 1 over GM plus RL over RO times GM. And right. So that's what we got for the input resistance. So now if we go back here, we found that, okay, so in this circuit here, we can write that our input resistance equal to if we write the whole equation will be RO plus RL divided by 1 plus GM RO. Okay, so that's the input resistance we found it. Now, of course, later on we're going to summarize that as well. Next, we're going to look at the short circuit gain. Why call it short circuit gain? Again, we're looking at output current because this is current input, current output. So we're looking at current gain, which means we define the current gain going to be AIS equal to output divided by input. Now, IO is short circuit current. So we're going to do that. So we short we still have the input. That's the equivalent circuit we had. And then we short the output. So now we have input current coming in and that. Now you look at this circuit, it's a very interesting circuit because the top is grounded and here's the ground too. So basically, you like the top circuit, you simply flip it. Move the ground to the bottom, what happens? You get all this connect to ground. This connect to ground, this connect to ground. Now the middle one is actually here. This one here is GM, VGS. It's GM times VGS. We can convert it into 1 over GM. Why? Why in this case we can? In the previous one we cannot. Because you look at what VGS is. So VGS is between G and S, but G is ground. So it's minus VS to ground over here. So therefore, that VGS is the same as the terminal voltage, right? So therefore, you can convert this one into 1 over GM. So basically, by converting that, you get this equivalent circuit to be something like, well, I'm not going to redraw this one because simply you have 1 over GM. Now we move this circuit, we just simply flip it. And nothing will change because it's ground. So the top, like here is ground, right? So we will simply draw like this here, the ground, and then we draw this one flowing to up though. And here we have this. And then this one up because of VGS. Now this S, this is G ground. So this becomes 1 over GM. So this one becomes Yeah, okay, so this is already here. It becomes the circuit over here. So what we need to find is IO, which if you look at the top circuit, IO is flowing to ground, but it's also same as in the middle, right? Because the current going from this two, going to other two, the middle part is IO is the same. So we have IO here. Now, if you look at this, it will be easy to calculate IO. How do you calculate IO? Because these two resistors are in parallel. So this circuit becomes and you can tell me this is a current divider, right? So this RS and this resistance is 1 over GM in parallel with RO. So this is the current resistance, which is IO is equal to the in current divider, you have RS plus in parallel with RO, and then the top is RS n times II. So your AI is equal to IO over II, which is equal to RS over RS plus 1 over GM in parallel with RO. So it becomes really simple to find that current gain. Just simply do this. Now, in this equation, we can manipulate in many different forms. Like we can divide RS, then we get one, we can divide this. But in the book, it basically eventually come to down to GM plus. The reason we do this is because we want to tell you a few unique things about it. Is GM all right. When we manipulate this equation up to this equation, we find that this 1 over RO is very small, and 1 over RS is also very small. The RS, for example, 10 kilo. So 1 over 10 means like 0.1. But GM is usually 1 to 10, or maybe even bigger. So therefore, these two terms eventually are very small, and they're very small, which means AI is almost 1. So a common gate amplifier becomes almost gain of 1, similar to a source follower. Yeah. Yeah.
What's the value of R naught?
You mean here? As 1. Yeah, 1. Yeah. Okay, sure. Let me make this. This doesn't look like 1. The reason you can convert GM over VGS into 1 over GM because the voltage from here to here is VGS. So use voltage divided by current, you got 1 over GM.
Oh, yeah. Current, yeah.
Right. So use both the terminal voltage divided by the current. Yeah. So that's why I mentioned earlier, you can convert only this voltage is VGS. If it's not VGS, you cannot do it. Yeah. Okay. So yeah. So I wrote everything on the slide. I thought I might not have enough space, but I did. So now we need to look at output resistance. To find output resistance, what we need to do is we need to apply a voltage at the output, find the current, and then derive the resistance. Now we need to keep this RS here because if without RS, we'll not be able to flow current. So therefore, we have to keep RS here. Doing this is actually fairly simple since this when we apply Vx, right? So you see here, you cannot convert this into 1 over GM anymore because the VGS is not the terminal voltage over these two terminals. So we can do a simple nodal analysis on this one to get it. So when we do nodal analysis, you see we have a current going down here, we're current going this way, we're current going this way, right? So the nodal analysis says that we need, in nodal analysis, we need to find the voltage over here, Vs. So let's find Vs. So Vs over Rs is the current going to the left hand? It's going to be equal to Gm times VGS, which is the current flowing down. And another current will be Vx minus Vs divided by Ro. So that's the nodal equation at this point. Basically, we have a nodal equation. Vs divided by Rs, give you current here, this current here, and this current is going to be Vo minus Vx minus Vs divided by Io. So we get the current in this branch. Now, in this nodal equation, you notice that we have Vx is supposed to eventually we're going to eliminate, but we do have two variables. One is VGS, the other one is Vs. So we need to be able to solve for Vs or VGS. We need to find out. In order to solve for Vs, we need to find VGS because VGS we don't know. Now look at this circuit. What do we have for VGS? So VGS is VG minus Vs. Well, we have Vs here, which means our VGS is going to be, so VGS is going to be Vg minus Vs is going to be minus Vs. So we simply plug in this one to here. We'll get Vs over Rs equal to Gm times VGS is minus Vs. So we're going to have minus sign here. And then we have plus Vx over Ro minus Vs over Ro. So in this case, we can find Vs. Do a little bit trick here, so make it easier to read. So this is, we have Vs in three terms, here, here, and here. So Vs over Rs plus Gm times Vs plus Vs over Ro equal to Vx over Ro, right? So now we have Vs equal to 1 over Rs plus Gm plus 1 over Ro equal to Vx over Ro. So we have Vs equal to Vx times like Ro times all these things together. So we have Vs found. Now once you find Vs, basically you can find Ix quickly because Ix equal to Vs over Rs, right? So therefore, our output is going to be Vx over Ix. It's going to be Ix is Vs over. It's going to be Vx over Vs. It's going to be Rs times Vx over Vs. So Vx over Vs, you find it here, right? So here we can find Vx from this equation here, or you multiply Ro on this side, you get Vx. So for Vx, and then we eliminate Vs, and this Rs. So basically, we can easily write this right in the next slide. No space here. So we can write R out from a previous slide. It's going to be Vx over Ix Ro times 1 plus Gm Rs plus Rs over Ro. And then right. So in this example, if we multiply Ro to the inside, we'll get, yeah, that's what, Ro plus Rs plus Gm Ro times Rs. We get three terms. Now this is a fairly simple output resistance. But the thing that we want to understand is that you have Ro, you have Rs, and then you have Gm Ro times Rs. So Ro, we can do example. Let's say if Ro is 50K and Rs, let's say we give the same 50K, and we get Gm is 1. And what do we get for R out? should be 50 plus 50 plus 1 times 50 times 50 equal 350, right? So typically, like this second term is roughly, actually, it's not too, no, actually, we are wrong. No, that's GM. Yeah, actually, it is right. GM is milli. Yeah, so 350. So the second term over here is the third term here is much larger than this one and this one, because this one is 250, that's 50, that's 50, usually about 10 times bigger. So usually 10 times bigger. So basically, if you neglect the first two terms, we see the resistance increase by GM times RO. So this is the increase the resistance by this much. So now let's summarize it. We're saying that input resistance is small, output resistance is large, and gain is almost 1. So that's what really we have done with the conclusion. So that's the original circuit. That's the equivalent circuit. And the middle is the equivalent circuit of the MOSFET. So let me draw. So this is your MOSFET. This is your input, and this is your output. So that's your MOSFET. So the input in the middle is a MOSFET. So we write down R in and R1 and R in IO and IS. We can write the actual expression is going to be RO plus RL divided by 1 plus GM RO, and output is going to be RS plus RO plus GM RO times RS, and input gain is, input gain is almost 1. So we can basically say that it's 1. So if we now plug in these numbers into this circuit, we can get the actual gain. Like if you add like a resistance here, you get over here. Now you can find the gain, everything. So it's fairly simple now by having the equivalent circuit. So in the book, you will find that they call this common gate amplifier has impedance transfer property. What do you mean impedance transfer? Well, because the gain is 1. So if you have an input and output the same, gain is 1, what are you doing with the circuit? So we basically transfer impedance, which means we decrease the input resistance and increase the output resistance. That's what we're doing. So that's called impedance transfer. And we already derived the input and output resistance. So the output resistance is that, and the input resistance is this. So that's the actual equation that we have. So in the future, if you see a common gate, you will simply replace the gate with impedance transformation equivalent circuit, and you'll be able to do a lot of things with it. Okay, so I think that's what we have. Now we can go back to the, so now let's go back to the common source amplifier. Remember, in the common source amplifier that we did earlier, we don't have a resistance RS over at the source, which is very easy. But once we have the RS over here, we, instead of using the pi model, we had to use the T model, and it was quite complex to find the gain. Now, by knowing now you have this impedance transfer property, instead of doing this very complex like pi model, T model, whatsoever, and we can use the impedance transfer property, and we can solve for the gain. So this one, actually, we can do like here. So let me, if we draw the equivalent circuit using the pi model, it will look like this. So basically, this is your equivalent circuit for the common source amplifier with the resistance at the source. In order to find the gain of this circuit, I mean, what we need to do, we apply voltage at the output. We apply voltage at the input, and then we find what is the output voltage, and then we get the gain. What's most important here is that we want to find out what is the output resistance. Like this is already written, but there's a way to figure out what is the output resistance. Basically, find the output resistance, we would apply a voltage here. Let's go Vx, and then we find Ix. So if we do that, you probably say, oh, this is almost the same we did before, right? So if we go back to the circuit here, see, that's exactly the same circuit. What are you talking about, right? So it's very simple. So that's why we can have we don't have to go again, just we derive, we'll get this one. And then if you simplify this one, like neglect this RS, because RS is really small, and then you will have this one could be quite large output impedance. Okay, so this is common source. This is the one that I'm not going to go too much in detail, because this is the same as our the common gate amplifier. The only difference is that this is BJT, but for BJT we have RPi. Right, so that, but the other one that you don't have RPi over here, so the gated ground, this is open circuit. So with RPi, you can still solve this circuit. It just becomes more complex, and the input resistance is going to be different. The output resistance are also going to be different. So the process is very complex. So what I really needed you guys is, okay, know the process, because the equation was so complex, we probably need a half hour to derive the equation. So I'm not going to spend the time to derive it here. Right, so we're going to just let it go. And here, you would see that we have the output resistance and input resistance all solved for you. And you can easily see the difference, where everywhere this kind of find out, this RPi. There's RPi. So there's RPi, and here there's a RPi. So everywhere there's RPi included. So that's and then similarly, for the common emitter amplifier with RE at the base, we can also find that the output resistance also increased quite a bit, because the impedance transfer property. So this is reasons are really just for you guys information. We're only, we're not gonna, it's not gonna be on the exams. Okay, so that's a good thing. But I think it's good for you guys later on to like spend maybe 5-10 minutes to read through the textbook and to understand what it is. You don't have to memorize it. You don't have to memorize the equation or anything, but just make sure that you understand the process and you understand the idea why they do it. So that's enough. Let's see what time it is now. Yeah, so let's go ahead to still have quite a bit of contents. In order to increase the gain of amplifier, we often need to do something. Like instead of doing a simple, like in the previous example, at the drain, we had a current source, right? So that's, and then we found already the gain was GM times RO1 in parallel with RO2. So for the simple one, like the previous one, we'll write down the previous one was and the current source over here. And the current source basically have RO2, right? And then here we have RO1. So basically your gain is minus GM times RO1 in parallel with RO2. And we know that if RO1 and RO2 are the same, we reduce the gain by half. So that's what we got earlier today. So in order to make sure that we don't decrease the gain, instead of using a current source at the drain directly, we're going to add another stage. And if you look at VG2 or Q2, what can you tell basically? So the output of Q1, is where? This is the input. Output of Q1 is over here. And that output of Q1 is connected to where? To the source of Q2. And the gate of Q2 is grounded. So what do you call this? The thing in the circle, comma gate. So comma gate amplifier. It's comma gate amplifier. So in fact, what we're doing is we basically use Q1 as a stage 1 amplifier, then we put the output of Q1 into Q2, we amplify again. So this is like 2-stage, but we don't call this 2-stage in the book. I mean, this terminology, we call this cascade. Cascade means cascaded. I forgot what. Transistor or something. It's like one on top of another. It's cascaded. So it's cascade. It's not cascade. It's cascade. So it's a word. If you ask people who did not study electronics, nobody knows what that word is. Actually, if you type this in Word, it says it's a wrong word because even Word does not have this in its dictionary. It's interesting, right? So it's a now since Q2 is a cascade. I mean, it's a common gate amplifier. You basically can say that, well, that thing I can do that as a impedance transform because the gain is 1, right? So it does not change the gain. But the output and impedance have changed a lot. So that's why this thing is so cool, right? So how do I do the analysis? Is I'm going to draw the equivalent circuit over here so that you can see it very easily. Yeah. So I'm going to draw the bottom one as so that's the bottom one. And in the middle, you have GM times VGS1, which is equal to GM times VI. And this is your VD1. Okay, so that's my bottom one. So my middle one, I can draw yeah. So I can draw it like this again. But my gate is the ground. So VO is to ground, okay? VO is to ground. So over here, you see, okay, let me write down the top. The top one is GM2 times VGS2, and VGS2 is here. So, and then I can now find VD1. We can do it together, guys. What is VD1? Right? So VD1 is this current is going this way. So RO1 times this gives you VD1. So the next one is to find VGS2. You guys and do it together. What is VG? How much is VGS2 in reference to other voltages? So VGS2 is VG minus Vs, which is ground. So 0 minus the voltage over here, which is the same as voltage over here. So VGS2 is 0 minus VD1 equal to minus VD1. So VGS2 is this. Oh, now we calculate VO. So you see the top one, you have current going down like this. So that circles through RO2, right? So which means you have current going this way, and the voltage over here will be minus GM2 times VGS2 times RO2. So if we plug in that VGS2 here, the negative sign is going to cancel. It's going to be GM2 times RO2 times VD1. And then it's going to be GM1 times GM2 times VI times RO1 times RO2. So now we got our A is going to be equal to VO or VI equal to GM1 times RO1 times GM2 times RO2. So basically, with the one that added on top, instead of the gain of GM1 times VO1, RO1, we increase that by GM2 times VO2. Do we miss a minus sign? The gain is minus GM, VGS2 is, yeah, so we miss a minus sign. So it should be minus. So basically, minus sign here, so it's going to be minus. So you see this gain is increased a lot. So let me, we're going to go to the next page. We're going to rewrite this. So basically what we are saying is this AV equal to minus GM1 times RO1 times GM2 times RO2. So this typically, if this transistors are identical, you basically make it really big. Like if it's 100, now it's like 10,000, right? So this is very useful in terms of our oh wow, I know what's wrong. Sorry guys, I made a huge mistake here. I'm terribly sorry. No, this is wrong. VO is not here. That's why I thought I should be. So VO is here. VO is here. VO is at the between D2. Oh no, it is between D2 and D1. No, it is between D2 and D1. Sorry. It is between D2 and D1. So it's in the O. Okay. I got it, that part wrong. Okay, yeah, no, I was looking at a different problem. No, this is correct. Okay. So what we're saying is we have AV, which increased quite a bit. So now we're going to do another example. Look at this source follower. Because the previous one, now if you look at this one can be considered as no, this was looking. I just want to make sure that we compare the same thing. So this one is input is over here. So this is a common source amplifier because that Q2 is like another stage of amplification. The input, so the input side, the input one is a common source amplifier. Now we're going to look at another one is source follower, which is a common drain amplifier. So in this common drain amplifier, you see the current source is at bottom, right? So the source is not grounded, but the drain is grounded. So we take the output at the source of the NMOS. So in this example, we can do, so this part here is a current source. So that can be replaced by simply just like previously we had a current source. Remember, we have output impedance gain of 1, right? So we can replace that with simply. So we will simply replace this Q3 as RO3. Now, of course, there's always like a DC biasing current, right? So this is like a DC current here. But when we do AC analysis, we can open that current source. So now you might say, well, this looks familiar, right? You will go back a few more slides. Let's see. Not very long ago, here. See, here we have, except the difference here is RS, but the other one is RO3. So it's very simple. So we don't have to do really much now because we already did that part. But we can still, in that case, we did not find, so what I want you to do is I want you to find maybe the output resistance of the circuit. So we can draw the equivalent circuit of this one. So now we have the equivalent circuit. So now we're going to draw the small signal of this one, which is equal to input, gate, So I think one of the mistakes that our student beginning to make is mixing Vin and VGS. But in this case, Vin is not VGS. Why? Because Vin is relative to ground, but VGS is from gate to source. So therefore, VGS is not Vin. It's very important. So Vin, VGS, okay, different things, right? So since they're different, we can find, like, depending on what we want to do. So in this case, for example, we can easily find input resistance. What is input resistance? So your input is basically like an open circuit. Therefore, your input resistance is infinity. So the next thing is that we want to find our gain and our output resistance of the whole circuit. Now, if we want to find the gain, we basically need to solve for VO in terms of V in so we can find the gain. In order to find output resistance, we need to connect the voltage at the output, basically here. We need to connect the voltage over here or over there, and to find, over here to find out how much current in there, and then we can find yeah. So let me do that. So in order to find the gain, we need to find VO. So the thing is that there's current going this way, but there's current going this way. So we can do the nodal analysis. We can do the nodal analysis at the source. So at the source, we have nodal analysis is going to give us VO over RO3 equal to so we need to find the current this way and the current this way, and then this current. Let me erase this. The current this way. So there's two current coming out, one current coming in. So this current is VO divided by RO3 plus this voltage VO divided by RO1 equal to GM times VGS. And we need to find VGS. So VGS equal to V in minus, see, V in minus VO, because our output is the source. The VGS is V in minus VO. So simply plugging this one into this equation over here, we'll get VO over RO3 plus VO RO1 equal to GM times V in minus GM times VO. Now we can move this VO. Yeah, we can move the VO to the other side. We can have VO equal to, yeah, so we have VO equal to 1 over RO3 plus 1 over RO1 plus GM equal to, oops, GM times V in. So our A is going to be VO over V in, VO over V in. So it's going to be GM over GM plus 1 over RO3 plus 1 over RO1. And this thing is going to be, because RO1 like it's much smaller than GM, and 1 over RO3 is much less than GM. So that's why we can say the voltage gain is almost 1. So this is why this name comes from, source follower. So at the source, we follow the gate. We follow the gate. But since the gain is 1, we don't get much benefit by using this circuit if we want to get the gain. So the advantage we got this is really the output resistance. So if we want to get the output resistance, let's go back to the equivalent circuit. So what we need to do is we need to look at, we need to apply a VO, a short input. So we need to short input. Here, so we draw the circuit again. So we need to short the circuit, and here. So So we need to short the circuit here, and then we can find IO over here, and our output voltage will be, output resistance will be VO over IO. So if we can find IO over here, we can find. Now, IO, one current going this way, and a current going this way. Now this is ground, so this is VGS. So we need, this is GM times VGS. So we need to find, again, a few things before we can do that. And the best way, again, is to do a nodal analysis on that point. So VO, right? So if you look at the nodal equation will look like VO divided by RO1 plus VO divided by RO3 equal to GM times VGS. And VGS equal to minus VO. Right now, we don't have any V in because V in is grounded. So we simply plug in this one to here. And then we got this output resistance. So let me see how much resistance is going to be. Eventually, what we got was the output resistance, our output equal to VO over IO equal to 1 over RO plus 1 over RO3 plus GM 1. So that's like, just like this three things in parallel. And in fact, if we go back to the circuit, you'll find that that is actually exactly true, because if you look at equivalent circuit again here, the top is ground, right? So we can basically flip the top to the bottom, and VGS, that is also ground. So therefore, you would get right. So you can get the circuit, if I redraw the circuit, and we can do it together. These things are becoming and this is all VO. So this circuit basically comes this way, and this is your ground. So your VGS. So you see what VGS is now exactly the same as the voltage at the two terminal. So your VGS divided by GM times VGS, that gives you 1 over GM, which is resistance. So now you have this. Right? So therefore, RO equal to 1 over R1 O1 in parallel with 1 over RO2 in parallel with 1 over GM. Okay, so now remember, RO2, RO1 are quite large. So therefore, this is like 50K example, and this is 50K. And the middle 1 over GM is 1 over 1, which means it's about 1K, right? 1 is milli. So 50K, 1K, when you put all this in parallel, those two 50K basically gone. So your output resistance is basically one over GM. What does it say? Output resistance is very small. So that's, to summarize our source follower, its two properties is small RO and unit. So by this time, I think some of you might already get confused. So earlier you said you want to increase the output resistance. So now you want to reduce the output resistance. What's the point? What are you doing? Well, the previous one, we tried to increase output resistance, we use that thing as a load. Here we decrease the output resistance because we used it as amplifier. Now let me give you example. So this just saying that to balance the previous circuit, we add like a resist here. So what do you mean? Like here, let's say you got an amplifier block, you got a load block, and you got an input. So in this case, the equivalent circuit is something like this. Let's say there's an internal resistance here. Or if we use a voltage source, it's easier. Because you can always convert a current source into a voltage source, okay? And this is your load resistance. Now look at this circuit. If your input resistance is too small, what happens? This will drop most of the voltage. So input doesn't really go here, right? So that's why we want input resistance to be small in circuit. But in this case, this is your output resistance. If your output resistance is too big, what happens? This doesn't get too much voltage. So therefore, we want output resistance to be small, input resistance to be big. So for amplifier, we want this one to be big, we want this one to be small. But if it's a load, if it's a purely load, like if this is your load, what do you want the load to be? If this is your load, you want your load to have as much resistance as possible because that's going to, okay, regardless how big is this one, if mine is big enough, I'll get all the voltage I need. So I'm not wasting anything. So that's why for load device, we want the impedance to be big. But for amplifier, we want output impedance to be small. So that's why we have sometimes we talk about big, sometimes we talk about small. And then we have a reason for that, okay? So I think this is good enough to stop. And then next week, I'm gonna I possibly review a little bit of this. And then we're gonna talk about very quickly Wilson and Wilder. There's two different current Widler current sources, and they're very unique, very useful. And then we'll go to example, spend about a half hour, and then we'll go to chapter 9. Okay? Yeah. This one?
Yeah, so are you able to overhaul this right here? Or will you just replace that with
Oh, that's because we did the current source analysis before. We find that the whole thing doesn't matter. Only this one, resistance matter.
Oh, because the current gain is 1 basically.
Yeah, the current gain is 1, yeah. Only the output resistance here. Yeah. That's why it's all connected. Right. So, as we move along chapter 9 and 10, and then you will slowly feel, yeah, all the things are going to connect together. All the pieces are going to connect. Yeah.
Thanks for
Huh?
Yeah. Sorry.
Oh, okay. Okay. Yeah. 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 Because remember, in the very beginning of the class, we derived the equivalent circuit. Remember, we derived this circuit, and we find out that only output resistance matters because the gain is 1, and we find that the gain is almost 1, and then the only the output resistance here, which means this part doesn't matter, only the resistance over here matters. Yeah. Yeah, with the iris, yeah, with internal resistance, yeah, the early resistance. Yeah, with small circuit model, and it will tell you, yeah, only that early voltage, early resistance matter, everything else doesn't matter.
And then the next quiz, the common base amplifier,
That's just today's, whatever we cover today. Yeah.
just focus.
Yeah.
the exercise.
Yeah.
For next week, so we don't have to worry about Wilson and.
Oh, no. Yeah, I'll post the slides with the notes and the lecture
Okay,
tonight if I have time.
thank you. But the solution is gonna be released, because honestly, I got like at least an 8, because I used the same equation, but for some reason I got a 6. I used the ratio for the first 3. I mean, I would think those were right, and then the other 3, like,